So in this case, let's use the bottom point A as reference. All right, so to save some time, I think I can solve these right now. So the same thing, T. In this case, you have a mass dangling. So the same thing, you don't have to worry about it. It should be the same kinetic energy. All right, then the potential energy, as I said, whenever you want to calculate potential, you need to find all the springs in the system and the gravity in the system. Here we do have a spring. Your U is half k x squared. So that's due to spring. Let's name it as U1. And then let's say your x equals to sine theta L. So eventually you have half k sine theta L squared. That's the potential energy associated with associated with spring. So the second part of your potential energy is due to gravity. So in this case, can you tell me what that is? So it's going to be mg theta h, right? So we just need to find where the theta h is. So in this case, we're lifting up the ball. So we're increasing the potential energy. So that's why the potential energy should be a positive value. And then your theta h will be 1 minus cosine theta times L. So basically, this narrow displacement is your theta h. Because we know the total length is L, and then what's left behind is L times cosine theta. So the difference is 1 minus cosine theta L. So you can plug it in, mg 1 minus cosine theta L. All right, eventually your U is all these potential energies summed together. You have a half KL squared sine theta squared. Let me put this theta squared plus mg 1 minus cosine theta L. All right, so your T minus U is your L. That gives you half ml squared theta dot squared minus half KL sine theta minus mgl plus mgl cosine theta. Okay, so again, calculate partial L, partial theta dot, the partial derivative with respect to velocity first. So only the first term has velocity in it. So that's ml squared theta dot. The same thing compared to the example before. And then one more time derivative. So your single dot becomes double dot, and all the others are the same. And then we need to calculate partial L, partial theta, the partial derivatives with respect to position. So only these terms have position in it. So let's calculate the first one. Remember, there is a negative sign in front. Okay, so it becomes negative KL squared time. Okay, let me express this out. Negative half KL squared, and then the 2 should be taken off, sine theta. And then you also have to do one more derivative with respect to sine theta. So you have a cosine theta afterwards. And then for the second term, cosine theta becomes minus sine theta. All right. So then you just go back to the Lagrange's method, and then you're gonna have ml squared theta double dot minus whatever in it. And then the half and the 2 times, they cancel out. That equal to 0. So that's eventually your solution.